All right, so where we left off, I'd just like to make sure you understand how to tell which acids are stronger, etc. So what if we were comparing HF, all the group 17 binary acids? We have HF, HCl, HBr, and HI. Out of these, how do I know what is the strongest acid? Well, you have to think about it. What's the definition of an acid? It's something that loses its proton. So which acid would lose its proton the easiest? Well, let's look at radius. They're all the same charges. Let's look at radius. This has very tiny radius, and this is very large. The larger the molecule, the easier it will be to lose a proton. So HI is your strongest acid, and then HF, oh, I'm sorry, this would be your got myself mixed up. So SI would be your strongest, and then HF would be your weakest. Sorry. All right, let's look at HF and H2O. And I know some of you think, oh, I know which one this is. It's HF easily, because H2O is just water. Well, what if you're comparing acids that aren't in the same group and you can't look at the radius? Then you want to look at electronegativity. So what is electronegativity? It's the atom's ability to attract electrons, right? So if we look at this and going down a group, the size of the atom increases, the HX bond strength decreases, and the strength of the binary acid increases. Okay, let's go across the period. As you go across the period, electronegativity increases. So F's there, and O's here, and N's here, as we go across the period. So electronegativity increases. This acid bond polarity increases because it's a larger difference in electronegativity. The strength of the acid increases. So the larger the difference in electronegativity, the stronger the acid. So HF would be a stronger acid. All right, let's do some more. Let's compare HIO, HBRO, and HClO. Ooh. What are we going to use here? We're going to use, I'm not going to tell you. You figure it out. Think about it for a second. Pause the video if need be. Look at a periodic table. Which one's stronger? HClO. ClO is more electronegative than Br and I. Okay? You can also, we'll just keep it like that. How about if we do HClO and HClO2 and HClO3 and HClO4? Which one's your strongest acid? Can't look at electronegativity because they're all the same. The only thing that changes is the number of oxygen atoms. The more oxygen atoms, the stronger the acid. And then the last one, can't look at electronegativity, can't look at number of oxygens. What are you going to look at? The number of hydrogens. The more hydrogens you have, the stronger acid it is. Strength decreases as the negative charge increases. Just an FYI. All right, we are ready to move on. Weak acids and bases. So if it's not one of those 6 strong acids or bases, it's weak. And you've been told that since the beginning of the year. This means that they do not ionize barely at all. We look at the Ka to tell us how much it does ionize. Set up the same way that our Kc, our Keq, our Ksp were set up. Products over reactants, and you ignore your solids and liquids. All right, so weak acids are going to have a Ka value less than 1. obviously, because they do not ionize that much. If we look at this right here, H2O is going to be a liquid. All these other things will be aqueous, so your Ka will be products over your reactants, all aqueous. Make sure to use brackets to show that we're talking about molarities. Here's some Ka values, which when we do some of these example problems, we will have to look at. So they want you to write the Ka expression for acetic acid. Well, you have to know what acetic acid is. Acetic acid is HC2H3O2, aqueous. It's going to be reacting with water, which is a liquid, and it's going to break apart into H plus aqueous plus C2H3O2 minus aqueous. The Ka, you would ignore water, so the Ka is just H plus concentration times the acetate ion concentration divided by the acetic acid concentration. All right, weak bases, bases without OH, react with water to produce hydroxide ion. Common examples are ammonia, which we've talked about all year, methylamine and ethylamine. And you can look how that forms right here. So this partial positive H on the water is attracted to the partial negative nitrogen on the ammonia. So this is going to be pulled over to make the NH4 ion, and then you have OH negative. And that's how that works. What's acting as your acid? Your water's acting as your acid because it's donating the proton. The ammonia is acting as your base. If you go the reverse, what's acting as your conjugate acid? It would be your NH4 plus, because when you go backwards, that is what's donating the proton, and this would be your conjugate base, because that is what is accepting the proton when you go the opposite way. So remember, bases have conjugate acids, and acids have conjugate bases. You can look at these other things as people that took a organic might recognize some of those things. Kb is set up the same way, products over reactants, but you won't have an H+, you'll have a hydroxide. And again, the Kb will be small because not a lot of product will be formed. Many weak bases do contain nitrogen. If you look at those couple examples at the bottom of the last page, it's because that nitrogen is going to be very attracted to that hydrogen. All right, so let's do this. The ammonia, we can write this again. It was on the previous page, but we'll just rewrite it. Something I may not have mentioned earlier, for all these weak acids and bases, you also want to show a double arrow. So your Kb would be equal to your ammonium ion concentration times your hydroxide ion concentration divided by your ammonia concentration. Ignore H2O because it's a liquid. All right, Ka and Kb look very similar. We've already talked about that. Talked about at the beginning how you will see the proton and hydronium ion used similarly. So if you don't have water, you won't have hydronium. Sometimes water's left out of your reaction. Even though it's still there, it's sometimes left out. So what I want you to do now is stop the video and let's compare acid strengths. Oops, even though you have the answers there, try to cover them up. And then we will figure this out. All right, so the first thing I did is I wanted to see where these ions and molecules were coming from. If they're bases, they came from acids. So this came from H3O+, this came from HF, HCl, HNO2, and HCN. Then I went to that table 14.3, and I found their, might have been 14.2, table 14.2, and I found their Ka values. And I know the weakest conjugate acid, so the smallest Ka value, would have the strongest base. All right. I also know that this is a strong acid. So this strong acid is not going to have a strong base. So I know right off the bat that Cl negative has to go last. And I also know that this H3O is almost as strong as a strong acid. So my H2O will be next. What do I do with these? Well, this is going to be my smallest Ka, so it's my weakest conjugate acid, which means it's my strongest base. And then look at the numbers comparing HF and HNO2, and that's how you get them. So Cn negative is your strongest base, and this is your weakest base. All right, let's move on. So you can read all this other stuff about the water molecule. It's pretty interesting. Water self-ionizes. So if you react a water molecule with a water molecule, you're going to get ions, the hydronium ion and the hydroxide ion. So one of these acids is one of these waters is acting as an acid, and one's acting as a base. If you go the opposite, this would be your conjugate acid, and that would be your conjugate base. Okay, there is a equilibrium constant expression for water. It's called Kw. And Kw at 25 degrees Celsius is always 1 times 10 to the negative 14th. Sometimes they give you a different Kw because they change the temperature. So Ka times Kb equals Kw. So if you know a Ka or a Kb, you always know your Kw, you can find the other one. Knowing these values allow us to calculate your hydroxide and hydrogen ion concentration. Best part of the chapter. So if your hydroxide and hydrogen are equal, it's neutral. So your pH is about 7. If your hydroxide ion is greater than your hydrogen ion, it's going to be basic. So that's going to be a pH of greater than 7. And this guy right here, if the hydroxide ion is less than the hydrogen ion, it's going to be acidic, so your pH is less than 7. Oh, yeah. All right, so let's do some work here. Let's figure out, it says it's 60 degrees, so they changed the temperature like I knew they would. The value of Kw is 1 times 10 to the negative 13. Using Le Chatelier's principle, predict whether the reaction below is exothermic or endothermic. So, let's look at this. We know at 25 degrees Celsius, your Kw is about 1 times 10 to the negative 14th. At 60 degrees Celsius, your Kw is 1 times 10 to the negative 13th. So, it is definitely endothermic. How do we know that? Because when we add heat, our Kw value increases, which means we're producing more products. So the reaction has to be going to the right. Equilibrium shifts to the right. So that means it has to be endothermic. Because remember, when it's endothermic, heat is written as a reactant. So they're adding more heat, which is pushing the reaction to the right. Calculate hydroxide and hydrogen ion in a neutral solution at Kw. Well, you know Kw equals H plus times OH negative. Kw is 1 times 10 to the negative 13th. It's neutral. For a neutral solution, you know your H plus and OH negative have to be equal. So just make these X. So 1 times 10 to the negative 13 equals x squared. Take the square root, and you find H plus and OH negative to be 3 times 10 to the negative 7. You're just solving for x. All right, some very, very important equations here. pH equals negative log of H. pOH equals negative log of OH. And pH plus pOH equals 14. You can use that scale right there to look at the different substances that are acidic or basic. I'm not going to do that. All right, I want to look at this. This is the most important part. Calculate either the H plus or OH from the information given. State whether the solution is acidic, basic, or neutral. All right, what I think is easier is just to find your H plus. All right, and compare it to your OH negative. Or you can find your pH. So it's at 25 degrees Celsius, so we know all of these. Kw equals H plus times OH negative. So for all these, 1 times 10 to the negative 14th equals your H plus. And let's do the first one. Let's substitute in our OH negative. This one, your H plus, came out to be 1 times 10 to the negative 9th. Okay, well, let's find out what our pH is. Our pH equals negative log of H, right? So the negative log of 1 times 10 to the negative 9th, and you don't even need your calculator for that, because it's easy math, it's just 9. So this one is basic. Well, if the OH is negative 7, do the same type of math. H plus has to be 1 times 10 to the negative 7, which means pH has to be 7, so it's neutral. And this guy right here, they're mixing it up. They're giving you your H plus. So 1 times 10 to the negative 14 equals your H plus. And let's look for your OH negative. We don't have to. Your OH negative is 1 times 10 to the negative 15. I'm just doing this one a little bit different. Well, let's compare our H plus. Is definitely greater than our OH minus, so it's acidic. Could have did that for all of these. Say I don't want to do that. Say I want to find my pH. pH is negative log of 10. Not going to come out. That's just going to be 1. So your pH comes out to be 1. So you know it's acidic just by looking at the pH. Say that you were given your OH. You could have used this equation. You could have used H plus. No, let's not do that. All right. Like, you can get a little bit crazy with these pH problems. You don't have to always do it my way. You can do it, if you did it a different way, that's fine. Do it whatever way works for you. All right. Exercise 7. Go ahead and stop it. I know you have the answers here, but I want you to try to figure out. They want you to calculate the pH and the pOH for both of these. We're going to do, why don't you try both of these? And we'll come back. All right, so up at the top, all it is plug and chug. Your pOH equals the negative log of hydroxide ion, so just plug in your hydroxide ion, and you get a pOH of 3. You know, pH plus pOH equals 14. You know your pOH, so just subtract to get your pH of 11. This you could do several different ways. I found my pH, it's 0. I used my pH plus pOH equals 14 to find my pOH of 14. And that's it. Down here, they gave you your pH of 7.41, so subtract to get your pOH of 6.59. Two new equations. And you might know this from calc. So your H plus is equal to 10 to the negative pH. Your OH concentration is equal to 10 to the negative pOH. So I just plugged in my pH and my pOH. My hydrogen ion came out to this, and my hydroxide ion came out to this. Did you have to do it that way? Nope. If you found your H plus, you could have also did H plus times OH minus equals 1 times 10 to the negative 14th, because it said it was at 25 degrees Celsius, and you could have solved for that. Let's look at this next one. Now we're starting to get into the nitty-gritty of this. So, HNO3. HNO3 is a strong acid. It ionizes into H plus NO3 minus. If the reaction is 0.1 molar, that means this is going to be 0.1 molar and this is going to be 0.1 molar because it ionizes 100%. So now we know our H plus and we know pH equals negative log of H plus. So the pH equals negative log of 0.1. So your pH equals 1. Same thing here, strong acid. This is 1 times 10 to the negative 10th, which means this is 1 times 10 to the negative 10th, which means this is 1 times 10 to the negative 10th. Your pH is equal to the negative log of your hydrogen ion concentration, so your pH equals 10. What if it wasn't a monoprotic acid? What if you had H2SO4? What if it decomposed into 2H plus SO4 minus 2? Hypothetically. What if this was 1 molar? Well, you have double this, so this would be 2 molar, and that would be 1 molar. You have to pay attention to those coefficients, stoichiometry. And the last one, it's a strong base, so you have to make sure you know what it ionizes into, and it ionizes into Na plus OH minus. So if this is 5 times 10 to the negative 2, this is also 5 times 10 to the negative 2. Now, here's where people make mistakes. They don't know what this ionizes into. If it's an acid, it's going to ionize into H plus and something. If it's a base, it's going to ionize into OH negative and something. All right, so now we have our pOH. So we know pOH equals negative log of 5 times 10 to the negative second. So our pOH comes out to 1.3. And then you know pH plus pOH equals 14. So 1.3. Oops. Back it up. pH plus 1.3 equals 14, so your pH equals 12.7. All right. Not bad, right? Still hanging in there? Still good. All right. That's it for this one. Hope you're doing okay.